Winds faster than hurricanes, storms larger than Earth, and rain made from diamonds are all happening right now somewhere in our solar system. Far beyond the calm night sky we see from Earth, giant planets hide violent atmospheres and deep internal worlds that scientists are still struggling to fully understand. In this episode, Relaxing Facts Studio explores the superheated clouds of Venus, the endless storm engines of Jupiter and Saturn, and the crushing pressure systems hidden deep inside Neptune and Uranus. Some of these planetary processes sound impossible at first. Yet spacecraft, telescopes, and laboratory experiments continue confirming that these extreme worlds are very real. Clouds on Venus circle the entire planet in about 4 Earth days, even though the planet itself needs 243 Earth days to complete one rotation. The movement is extreme. Winds near the upper atmosphere can exceed 220 miles per hour, making them some of the fastest planetary winds in the solar system. Yet the rocky surface below barely turns at all. This effect is called atmospheric superrotation, and scientists still debate exactly how Venus maintains it for so long. That motion begins high above the surface, where thick sulfuric acid clouds absorb sunlight and trap heat unevenly across the atmosphere. Warm gas rises near the equator and flows toward colder regions, creating enormous circulation cells. The process behaves like a global heat engine. Unlike Earth, Venus has an atmosphere made mostly of carbon dioxide, and surface pressure reaches about 92 times Earth's atmospheric pressure. A human would experience pressure similar to being nearly a kilometer underwater. The strange part is how disconnected the atmosphere seems from the planet underneath it. Venus rotates so slowly that one Venusian day lasts longer than its entire year. Normally, friction between a planet's surface and atmosphere slows large wind systems over time. Venus behaves differently. Powerful atmospheric tides, driven by solar heating inside the cloud layers, appear to continuously transfer momentum through the atmosphere. The surface barely moves. The skies never stop racing. Higher in the atmosphere, the entire circulation system stretches across nearly 40,000 miles of cloud tops, wrapping around the planet like a permanent hurricane. Jet streams form at multiple altitudes and interact with thermal waves moving through dense gases. Some waves may originate from mountain ranges buried beneath the clouds. Even robotic probes survive only briefly there. Soviet Venera landers recorded temperatures near 900 degrees Fahrenheit before failing within hours. Those conditions make Venus one of the most difficult planets to fully understand despite being Earth's nearest planetary neighbor. Scientists can track cloud motion from orbit, but the deeper atmosphere remains difficult to measure directly because radio signals, heat, and pressure interfere with instruments quickly. The result is a planet where the atmosphere moves faster than the world itself, powered by mechanisms that are still only partially understood. Storms on Jupiter can grow larger than Earth and remain active for centuries without weakening. The most famous example is the Great Red Spot, a rotating vortex wide enough to swallow our planet completely. Winds around its outer edge can exceed 400 miles per hour. Saturn produces similar extremes. Near its north pole, Clouds organize into a giant hexagon nearly 20,000 miles across, forming one of the strangest weather systems ever observed. Those storms survive because gas giants do not behave like rocky planets with solid surfaces interrupting atmospheric flow. Jupiter and Saturn are mostly hydrogen and helium, and their visible clouds float above deep layers of compressed gas. Heat rises continuously from the planet's interiors, feeding powerful convection currents. The process creates long atmospheric jet streams moving in opposite directions. These bands trap storms between them, reducing friction and preventing smaller systems from tearing the larger vortices apart. On Earth, hurricanes weaken after moving over land or colder water because their energy supply becomes unstable. Jupiter's atmosphere has no continents and almost no solid boundary near the cloud tops. The energy source remains active constantly. Even lightning storms there can tower far higher than terrestrial storms. Saturn adds another difference. Its polar hexagon is not a single spinning storm but a standing wave pattern, shaped by high-speed winds circulating around the pole. Deeper below the visible clouds, pressure increases rapidly and transforms hydrogen into dense fluid states that behave very differently from gases on Earth. Some jet streams extend thousands of miles downward into the atmosphere. Spacecraft measurements suggest Jupiter radiates nearly twice as much energy as it receives from the Sun, helping sustain its enormous weather systems. The scale is difficult to imagine. Entire planetary climates operate like engines larger than all Earth's oceans combined. Those conditions reveal that giant planets store and redistribute heat far more efficiently than scientists once expected. Researchers can observe the upper clouds directly, but the deeper circulation systems remain partially hidden beneath thick atmospheric layers. That limitation matters because the storms may connect to processes occurring thousands of miles below the visible atmosphere. The longer these vortices survive, the more they challenge existing models of planetary weather and fluid dynamics. Far below the clouds of Jupiter and Saturn, pressure becomes so extreme that ordinary hydrogen begins changing into something entirely different. The gas is squeezed until its atoms can no longer hold electrons normally, allowing electricity to move freely through the material. Hydrogen starts behaving like liquid metal. Scientists call this state metallic hydrogen, and it may exist in enormous layers surrounding the deep interiors of giant planets. That transformation happens because gravity compresses the lower atmosphere with tremendous force as depth increases. Inside Jupiter, pressures may exceed 4 million times Earth's sea level atmospheric pressure. Temperatures also rise to thousands of degrees. Under those conditions, hydrogen loses many properties associated with normal gas behavior. The material becomes electrically conductive. Moving conductive fluids generate magnetic fields through a mechanism called the dynamo effect, the same fundamental process operating inside Earth's molten core. Earth produces its magnetic field using circulating liquid iron beneath the crust. Gas giants appear to rely on metallic hydrogen instead. The difference creates magnetic systems vastly larger and more powerful than Earth's. Jupiter's magnetosphere stretches millions of miles into space and traps intense radiation around the planet. Some of its magnetic storms would overwhelm unprotected spacecraft electronics quickly. The visible cloud tops only reveal a thin outer layer above these deeper internal systems. Beneath the upper atmosphere, the internal structure may contain multiple hidden layers transitioning from molecular hydrogen to metallic hydrogen and possibly denser rocky material near the center. Some estimates suggest the metallic region inside Jupiter could extend across tens of thousands of miles. The pressure is unimaginable. A single cubic inch of metallic hydrogen would likely weigh far more than most metals commonly found on Earth. Those hidden layers remain difficult to study directly because no spacecraft can survive deep enough to measure them. Scientists instead analyze gravity fields, magnetic distortions, and wave patterns moving through the planet's atmospheres to estimate what exists below. The challenge is significant. Metallic hydrogen has only been produced briefly in laboratory experiments on Earth, meaning much of Jupiter and Saturn's internal behavior still depends on indirect evidence rather than direct observation. Deep inside Neptune and Uranus, pressure may become strong enough to crush carbon-rich compounds into solid diamonds. Scientists believe these planets could experience continuous diamond rain falling through hot internal layers beneath the visible atmosphere. The process begins thousands of miles below the cloud tops, where methane molecules break apart under extreme compression. Carbon atoms separate from hydrogen and may reorganize into crystalline structures. In simple terms, parts of these planets could literally manufacture diamonds naturally. That transformation happens because ice giants contain large amounts of water, ammonia, and methane mixed beneath their outer atmospheres. Despite the name, these materials do not exist as normal ice there. Temperatures can rise above several thousand degrees Fahrenheit while pressure climbs millions of times higher than Earth's atmospheric pressure. Under those conditions, carbon atoms bond tightly into diamond structures. Laboratory experiments using shock waves and high-powered lasers have briefly recreated similar compression effects on Earth. Jupiter and Saturn contain mostly hydrogen and helium, which creates very different internal behavior compared to Neptune and Uranus. Ice giants appear richer in heavier volatile compounds instead of deep metallic hydrogen dominating most internal layers. Their magnetic fields also behave strangely. Rather than forming neatly around the planetary centers, the magnetic fields tilt sharply and shift away from the core. Scientists suspect unusual conductive fluid layers deep inside the planets may cause this instability. Far beneath the upper clouds, the internal structure may contain massive superheated oceans mixed with compressed fluids moving under enormous pressure gradients. Some models suggest diamonds could sink slowly toward deeper thermal layers before partially melting again. The scale is enormous. A single storm system on Neptune can approach the size of Earth while winds exceed 1,200 miles per hour, making them the fastest sustained winds measured anywhere in the solar system. Those hidden interiors remain largely mysterious because no spacecraft has ever entered deeply enough to observe these processes directly. Most current models depend on gravity measurements, magnetic field analysis, and laboratory simulations reproducing planetary pressures for fractions of a second. That limitation matters because Neptune and Uranus may represent one of the most common planetary types in the galaxy. Understanding their interiors could reshape how scientists explain the formation of distant exoplanets orbiting other stars. From the crushing pressure beneath Neptune to the planet-wide storms of Jupiter and Saturn, the giant worlds of our solar system continue revealing systems far stranger than early astronomers ever imagined. Even now, many of these hidden layers remain beyond direct observation, waiting for future missions and better instruments to uncover what is really happening deep below the clouds. Thank you for watching Relaxing Facts Studio. If you enjoyed this episode, please subscribe, like the video, and share it across your social media pages to help more people discover the channel. Leave a comment below with your thoughts and theories. Your support truly keeps this channel growing and alive.